Will the history of astronomy be divided between before Webb and after Webb?
Yes, I believe it will be.
The universe is full of puzzles, but perhaps none are more disquieting than the subtle, stubborn mismatches in the numbers that are supposed to describe its very fabric. This may not seem like a big deal, but it actually is. Despite decades of refinement, key cosmological values, such as the rate of cosmic expansion, are simply refusing to agree, no matter how precise the measurements or how sophisticated the instruments. This isn't just a matter of statistical noise, it's a whisper from the cosmos that something fundamental might be missing from our model of reality. This is going to hurt. This new James Webb Telescope discovery will shake up Einstein's cosmological theory. Scientists are also beginning to suspect that dark matter and dark energy may not be the whole story, and that some unknown force or phenomenon could be quietly rewriting the rules of the universe. So, is the way we look at the universe about to change? Well, let's dig in. James Webb Space Telescope and its transformative impact. When the James Webb Space Telescope launched aboard an Ariane 5 rocket on December the 25th, 2021, from French Guiana, it wasn't just the culmination of over 2 decades of meticulous engineering and international collaboration. It was the beginning of what many astronomers now consider a new era in humanity's understanding of the cosmos.
I'm very excited to follow the James Webb Space Telescope's launch with you all from space.
Positioned at the Sun-Earth L2 Lagrange point, about 1.5 million kilometers from Earth, the $10 billion telescope became operational in July 2022 and immediately began returning images and data that would upend long-held assumptions. With its 6.5-meter gold-coated beryllium mirror and instruments sensitive to infrared wavelengths, the JWST allows astronomers to peer deeper into space and therefore further back in time than ever before, capturing light emitted more than 13.4 billion years ago. What it revealed in its first year alone was so astonishing that researchers like Dr. Andrei Kudzo of the Institute for Theoretical Astrophysics have suggested a historical divide in astronomy itself, the age before Webb and the transformative epoch after Webb. This is big, huge. What this means is that the universe is nothing like what we thought it was. Within just weeks of becoming operational, JWST began to detect galaxies that appeared to form far earlier than any models of cosmic evolution had predicted. For instance, in July 2022, a study based on JWST data found candidate galaxies at redshifts greater than 10, suggesting their formation occurred within the first 300 million years after the Big Bang. These early galaxies were not only surprisingly numerous, but also unexpectedly bright and massive, indicating that the universe's initial conditions may have allowed for faster and more efficient star formation than previously thought. This directly challenged the prevailing lambda cold dark matter model, which had been the cornerstone of cosmological theory for decades. Researchers began reassessing how dark matter might cluster and how baryonic matter could cool and condense into stars, with some proposing that early star formation rates may have been underestimated by as much as a factor of 10. Another area where the JWST has proven revolutionary is its detailed spectroscopic analysis of exoplanet atmospheres. In November 2022, it successfully detected carbon dioxide in the atmosphere of WASP-39b, a hot Saturn-like gas giant located approximately 700 light-years from Earth, marking the first unambiguous detection of this gas in an exoplanetary atmosphere. Later studies unveiled the presence of water vapor, sulfur dioxide, and even hints of photochemical smog, revealing atmospheric chemical processes far more complex than previously assumed. These findings challenged prevailing models of planetary formation, especially regarding how exoplanets form, migrate, and interact with their host stars. By late 2023, JWST had characterized the atmospheres of more than a dozen exoplanets, ranging from gas giants to mini-Neptunes, and was beginning to target smaller, rocky worlds, especially those located in the habitable zones of nearby stars. In early 2024, JWST achieved another major milestone by analyzing the atmosphere of TRAPPIST-1c, one of the 7 Earth-sized planets orbiting the ultra-cool dwarf star TRAPPIST-1. Using the mid-infrared instrument, scientists confirmed that TRAPPIST-1c lacks a thick carbon dioxide-rich atmosphere, offering critical constraints on habitability and the role of stellar activity in atmospheric erosion. More recently, in early 2025, JWST observed the atmosphere of GJ 1214b, a super-Earth approximately 48 light-years away, during a rare secondary eclipse event. For the first time, astronomers were able to directly measure thermal emission from the planet's dayside and identify a high-altitude haze layer rich in complex molecules, including possible hydrocarbons. This groundbreaking observation marked the closest scientists have come to detecting prebiotic chemistry in a world beyond our solar system. JWST is now a critical pathfinder in the search for biosignatures. It is only a matter of time. We are closer than ever to finding life outside our planet. Beyond the discovery of ancient galaxies and exotic exoplanets, JWST has also offered unprecedented glimpses into stellar nurseries and the life cycle of stars. Its infrared vision has pierced through dense cosmic dust clouds to capture the birth of stars in nebulae, such as the Pillars of Creation in the Eagle Nebula and the Tarantula Nebula in the Large Magellanic Cloud. These images, released between late 2022 and mid-2023, revealed intricate details about protostar formation, accretion disks, and jet outflows, dramatically improving upon what was possible with the Hubble Space Telescope. Such data allowed astrophysicists to refine models of stellar evolution, shedding light on how metallicity and environment influence a star's birth and death. Andrei Kudso and others have noted that the unexpected complexity of these star-forming regions challenges previously held beliefs that stellar nurseries followed relatively uniform pathways. The James Webb Space Telescope has revealed a cosmos more chaotic, layered, and dynamic than the one described in textbooks just a few years ago. It has completed more than 1,500 science programs and continues to collect approximately 58 gigabytes of raw data per day. From detecting shockwaves in galaxy mergers to identifying the chemical fingerprints of elements forged in the earliest supernovae, JWST has prompted a widespread scientific reckoning. For many scientists, it is no longer a question of whether the telescope has changed astronomy, but just how deep those changes will go and whether we are equipped to comprehend the vast new frontier it has laid bare. We are indeed looking at a new frontier. For instance, we now have a very different outlook on how early galaxies were formed. Early galaxies challenge existing theories. In 2023, astronomers working with data from the James Webb Space Telescope examined a sample of over 30,000 early galaxies, some dating back to less than 500 million years after the Big Bang, and found patterns that defy the predictions of established cosmological models. These galaxies appeared to be far more massive, compact, and mature than the standard lambda, cold, dark matter model would allow for in such a short span of cosmic time. Many exhibited well-formed structures, such as disks and bulges, that were previously believed to take billions of years to emerge. The statistical spread and clustering of these early galaxies did not match the rate of cosmic expansion derived from observations of the cosmic microwave background and Type 1a supernovae, which are powerful stellar explosions that occur in binary systems when a white dwarf accumulates enough mass to trigger runaway nuclear fusion, serving as standard candles for measuring cosmic distances. This discrepancy raises serious questions about whether the underlying assumptions about the universe's growth over time were flawed or incomplete. further deep field imaging and spectral surveys using JWST's near-infrared camera, or NIR-CAM, and near-infrared spectrograph, or NIR-SPEC instruments led to a second, independent analysis published in early 2024, which focused on an additional 20,000 galaxies across various cosmic epochs. This follow-up not only confirmed the anomalies, but also provided clearer insight into the nature of the discrepancies. Galaxies at high redshifts were found to be forming stars at rates that implied either an acceleration of galaxy assembly processes or, more controversially, an error in the inferred distance and timescales derived from redshift measurements themselves. Several galaxy candidates were identified with inferred stellar masses approaching 100 billion solar masses at redshifts greater than 10, which means that they existed when the universe was only 500 million years old. This finding requires either a rethinking of how matter aggregated in the early universe or a revision of the interpretation of redshift as a reliable cosmic yardstick. These results have added weight to arguments suggesting that either the rate of cosmic expansion is not constant, or that the metric expansion of space may not be the correct framework at all. But wait, there's more: the Big Wheel Galaxy, a massive anomaly. Among the most startling discoveries made by the James Webb Space Telescope is a colossal galaxy now dubbed the Big Wheel, whose light has taken more than 12 billion years to reach Earth. The Big Wheel is estimated to have formed just 1.8 to 2 billion years after the Big Bang, when the universe was barely 15% of its current age. What makes this galaxy so remarkable is not merely its age, but its scale and structure. With a diameter exceeding 150,000 light-years and a rotational velocity comparable to the Milky Way, or even larger modern superspirals, it has forced astronomers to rethink the timeline of cosmic assembly. According to prevailing theories, galaxies from this early epoch should be significantly smaller, more chaotic, and lacking the well-defined disks and bulges seen in the mature galaxies of today. Yet, the Big Wheel exhibits an advanced level of organization that seems extremely odd. The mass of the Big Wheel is another anomaly. Current models suggest that massive galaxies take billions of years to accrete their mass through hierarchical merging, which involves small proto-galaxies combining over time. However, the Big Wheel appears to contain over 500 billion solar masses in stars alone, implying that either star formation and matter consolidation in the early universe occurred far faster than expected, or that our understanding of those formative cosmic periods is fundamentally flawed. High-resolution spectroscopy from JWST's NIR-SPEC instrument confirmed not only the galaxy's size and age, but also its well-defined rotational curve, indicating a stable disk structure that challenges the long-held belief that early galaxies were dominated by turbulent starbursts and erratic mergers. Instead of a chaotic, embryonic system, the Big Wheel appears to be an advanced, settled entity, existing in an era when such formations were believed to be extremely rare or outright impossible. The implications of this single discovery ripple through multiple layers of cosmological theory. The Big Wheel doesn't merely strain the limits of the lambda cold dark matter model. It questions whether the formation of large-scale structures in the universe occurred through the mechanisms we thought it did. Researchers have begun considering whether dark matter behaved differently in the early universe, or whether unknown processes such as rapid cooling pathways or exotic particle interactions could have accelerated galactic evolution. Some theories even entertain the notion that our observational models, particularly those related to distance and light interpretation in deep space, may need to be recalibrated to account for phenomena we do not yet fully grasp. As of early 2025, the Big Wheel is one of the largest and most mature galaxies ever detected from that epoch, a solitary titan spinning serenely through a young cosmos that was supposed to be disordered and embryonic. Its very existence is a profound cosmic contradiction. That is, we have only just begun to understand the true nature of the early universe. Multiplicity of massive early galaxies. In what many researchers now call a cosmological crisis, Webb has detected multiple massive, well-formed galaxies dating back to less than 500 to 700 million years after the Big Bang. These galaxies, some of which have been catalogued with stellar masses rivaling or exceeding that of the Milky Way, appear to possess mature structures, dense stellar populations, and in some cases even signs of rotating disks. What stuns astronomers is the sheer multiplicity. Instead of a single outlier that could be written off as an observational fluke, the telescope has found dozens of such candidates in various deep field surveys like Cosmic Evolution, Early Release Science, or SEERS, and JWST, Advanced Deep Extragalactic Survey, or JADES. Their frequency and maturity directly challenge the standard model of hierarchical galaxy formation, which predicts that the first galaxies should have been small, irregular, and slow-growing. One particularly disruptive dataset comes from a February 2023 study led by Ivo Labar and Erica Nelson, which presented 6 candidate galaxies from the JADES survey estimated to have formed within 500 to 700 million years post-Big Bang. These galaxies were found to have stellar masses of 10 billion to 100 billion solar masses, comparable to the Milky Way, at an epoch when galaxies were thought to be assembling their first stars. The gravitational and thermodynamic processes needed to achieve such rapid and massive star formation within such tight timescales are not accounted for in current lambda cold dark matter cosmology. Additionally, models incorporating the cosmic microwave background, nucleosynthesis, and early dark matter interactions struggle to reconcile how gas could have cooled, condensed, and ignited so efficiently in a universe still reeling from its primordial expansion. The theoretical timescales for matter to collapse under gravity and trigger starburst activity are simply too long, and thus fail to explain these galaxies' apparent maturity. The implications are staggering. If these galaxies are confirmed via spectroscopic verification and fine-tuned mass measurements, then the early universe was a vastly more productive and structured environment than previously imagined. Theorists are now contemplating a revision of the galaxy formation paradigm itself, with suggestions ranging from exotic dark matter interactions to modifications of inflationary theory. Some have proposed that the growth of early supermassive black holes may have played a catalytic role, while others suggest that cosmic variance and previously unseen physical laws may be at work. Speaking of dark matter, there's a new frontier opening up here as well. Dark energy, new revelations and challenges. Originally introduced to explain the accelerating expansion of the universe, dark energy has long been treated as a cosmological constant, a fixed, unchanging force embedded in the fabric of space itself. But recent data from Webb's high-precision surveys is prompting a radical reassessment. Observations of early galaxies, large-scale structures, and gravitational lensing patterns have hinted that dark energy might not be constant after all. Instead, it could be dynamic, evolving with time, growing stronger or weaker across cosmic epochs. This idea threatens to upend more than 2 decades of cosmological consensus that began with the Nobel Prize-winning discovery of the universe's accelerated expansion in 1998. One of the strongest pieces of evidence fueling this challenge is the discrepancy between the Hubble constant measured through local observations, such as those involving Type 1a supernovae, and the value inferred from early universe data like the cosmic microwave background. Webb's unprecedented infrared sensitivity allows astronomers to measure the expansion rate of the universe during a crucial, previously inaccessible window, between redshifts 3 to 10 when the universe was in its early formative stages. In this range, preliminary Webb data suggests a possible deviation in how expansion unfolds, which may indicate that dark energy's behavior is not static but responsive to changing conditions in the evolving universe. If this trend continues to be observed in further datasets, it would signal the need for a revised cosmological model, one in which dark energy is governed by a yet unknown field or force. Such a discovery would have seismic implications for theoretical physics. For over a century, Einstein's cosmological constant served as the simplest explanation for a repulsive energy permeating all of space. But if dark energy turns out to be dynamic, physicists would need to go beyond Einstein's general relativity and possibly enter the domain of quantum field theory or even string theory to make sense of it. Others speculate that what we interpret as dark energy might actually be an emergent phenomenon arising from the interaction of gravity with quantum vacuum fluctuations on large scales. But how did we get to this point to begin with? Well, for that, we need to walk through the corridors of history. In 1998, two independent teams of astronomers, the Supernova Cosmology Project and the High-Z Supernova Search Team, delivered a discovery so unexpected that it upended the foundational assumptions of cosmology. By studying distant Type 1a supernovae, which serve as reliable standard candles for measuring cosmic distances, researchers determined that these stellar explosions were dimmer than they should have been if the universe's expansion were slowing down. Instead, the results pointed to the expansion of the universe was not decelerating due to gravity, as had long been presumed, but was in fact accelerating. To account for this unprecedented acceleration, scientists invoked a mysterious force, an unknown form of energy permeating all of space. This came to be known as dark energy. This revelation fundamentally changed the architecture of modern cosmology. Before 1998, the prevailing expectation was that after the Big Bang, the combined gravitational pull of all the matter in the universe would gradually slow its expansion, potentially halting it altogether in a big crunch. Instead, the discovery of accelerating expansion implied that gravity was being outpaced by something else, something repulsive and persistent. This led to the revival of a concept Einstein had once introduced and then abandoned: the cosmological constant. The new force became the dominant component of the universe's energy budget. Current models suggest that dark energy constitutes nearly 68% of the total energy content of the cosmos, with dark matter making up around 27% and ordinary baryonic matter, the atoms that form stars, planets, and people, just 5%. The impact of this discovery rippled through the scientific community, prompting a cascade of new theoretical efforts and observational campaigns. Major space missions like the Planck satellite, the Dark Energy Survey, and now the James Webb Space Telescope were, in part, driven by the quest to understand this dominant but invisible force. The 1998 breakthrough earned Saul Perlmutter, Brian Schmidt, and Adam Rees the 2011 Nobel Prize in Physics. Yet, the precise nature of dark energy remains elusive. Whether it is truly constant, as Einstein's formulation suggested, or dynamic and evolving, as emerging data from JWST and other observatories now hint, remains one of the most profound and unsettled questions in all of science. For now, all we can do is wait, and while we wait, there's more. Recent conflicts and the Hubble tension, the ongoing debate over the true nature of cosmic expansion, has grown more intense in recent years, fueled by a phenomenon now widely known as the Hubble tension. This is the persistent and growing discrepancy between two different methods of measuring the expansion rate of the universe, known as the Hubble constant. Measurements taken from observations of nearby objects, such as Cepheid variable stars and Type 1a supernovae, yield a higher rate of expansion, about 73.3 kilometers per second per megaparsec, while those extrapolated from the early universe, particularly from the cosmic microwave background as measured by missions like the Planck satellite, suggest a slower rate of around 67.4 kilometers per second per megaparsec. The gap between these figures has refused to close despite increasingly precise measurements. Into this already tense landscape entered the Dark Energy Spectroscopic Instrument, or DESI, a project designed to chart the expansion history of the universe by mapping the redshifts of over 30 million galaxies and quasars. In its early findings, DSI identified unexpected inconsistencies, hints that dark energy's effects might not have remained constant over time. The initial reaction from many in the scientific community was cautious. Such deviations were often chalked up to methodological noise, incomplete datasets, or local variations in galaxy distributions. However, this skepticism has become harder to maintain in the face of independent, high-resolution data emerging from the JWST. Webb's precision observations have begun to reinforce DESI's hints, showing anomalies in the rate of cosmic expansion at different epochs that cannot be reconciled by current models assuming a static form of dark energy. The Webb data, which includes the distribution and structure of galaxies formed just 300 to 400 million years after the Big Bang, not only matches the scale of the DSI anomalies, but extends their implications to far earlier periods of cosmic history. This overlap is forcing cosmologists to seriously consider that what we've been calling dark energy might not be a single, unchanging force at all. The possibility that dark energy evolves over time could mean the standard lambda cold dark matter cosmological model needs revision or even replacement. What was once dismissed as noise is now being recognized as potentially groundbreaking evidence that the universe is governed by rules more complex than Einstein's general relativity and the cosmological constant can account for. This convergence of findings from DSE and JWST has transformed what was once a niche disagreement into a defining scientific conflict of our time, one that could soon rewrite our understanding of how the universe began, how it behaves, and ultimately, how it might end. Rethinking Einstein's cosmological theory, one of Einstein's most profound contributions to cosmology, was the introduction of the cosmological constant, a term he initially added and later retracted to preserve the idea of a static universe. As noted earlier, the cosmological constant found new life in 1998, when astronomers discovered that the universe's expansion is accelerating, a phenomenon attributed to a mysterious force later dubbed dark energy. This became a central pillar of the lambda cold dark matter model, the standard framework for understanding cosmic structure and evolution. But Webb's data, with its unprecedented resolution and depth, is casting serious doubt on the idea that dark energy is truly constant, and by extension, on the completeness of Einstein's vision of cosmic balance. If dark energy evolves over time, then the equations that govern cosmic expansion must be rewritten, or at least significantly modified. Einstein's general relativity may still hold locally, where gravitational forces are strong, but at cosmic scales, an expanded framework may be needed. This opens the door to so-called modified gravity theories, or even exotic concepts like emergent space-time, where the geometry of the universe is not fixed, but arises from quantum processes. Some physicists are revisiting earlier, marginalized models such as quintessence, which proposes a dynamic, changing form of dark energy that behaves differently across time and space. Others are exploring links between dark energy and quantum fields, or even extra dimensions, potentially bringing cosmology and quantum mechanics closer together. Looking ahead, the future of cosmology appears poised for a conceptual renaissance. The James Webb Space Telescope is only at the beginning of its mission, and already it has rewritten chapters of astrophysical history. As more data pours in, from Webb, DSI, Euclid, and upcoming missions like the Nancy Grace Roman Space Telescope, cosmologists anticipate not just adjustments to current models, but perhaps the birth of entirely new paradigms. So, what can we expect from the next chapter in this saga? What comes next? Even as the scientific community continues to unravel the wealth of data already provided by the JWST, the future of space telescopes promises to be equally transformative. The advancements made by the JWST will not only influence the design and capabilities of the next generation of space observatories, but will also shape our understanding of the cosmos in ways we are only beginning to comprehend. The next major observatory scheduled to join the space exploration effort is the Nancy Grace Roman Space Telescope, or ROMAN. Named after Nancy Grace Roman, the first chief of astronomy at NASA, the Roman Space Telescope is expected to launch in the mid-2020s, and it promises to complement the capabilities of the JWST by focusing on different aspects of space exploration. One of the key objectives of the Roman Space Telescope is to study the phenomenon of dark energy. While the JWST has made significant strides in investigating the early universe and the formation of galaxies, the Roman telescope will focus on more expansive cosmological questions, such as the exact nature of dark energy, which drives the accelerated expansion of the universe. Roman's wide-field imaging capabilities, especially in the infrared, will allow it to map large portions of the universe with unprecedented detail, allowing scientists to observe the large-scale structure of the cosmos. The telescope is designed to study galaxy clusters, galaxy evolution, and the physics of supernovae, particularly Type 1a supernovae, which act as standard candles for measuring distances in the universe. The Roman Space Telescope will also enhance our understanding of exoplanets. With its ability to survey large swathes of the sky, it will work in tandem with the JWST to deepen our knowledge of exoplanet atmospheres and search for signs of habitability in distant worlds. Unlike the JWST, which can capture high-resolution images of individual exoplanets, Roman's wide field of view will allow for more extensive surveys of exoplanet populations, improving our understanding of their distribution and the factors that govern their formation and evolution. Despite the enormous amount of data already gathered by the JWST, many of its findings remain in the early stages of analysis. Several areas of investigation are poised to evolve into groundbreaking discoveries, offering us deeper insights into the cosmos while raising new questions that will push the boundaries of human understanding. The JWST's observations of galaxies dating back to redshifts greater than 10 have reshaped our understanding of the universe's early stages. We now know that galaxies were forming much earlier than previously thought, and the process of galaxy assembly was more complex and varied than the simpler models suggested. Some of these early galaxies appear to have well-defined structures, defying previous predictions that the first galaxies would be small and chaotic. The ionization epoch, the period when the first stars and galaxies ionized the surrounding hydrogen gas, is another area where JWST's findings are pushing our understanding. Astronomers are still piecing together how quickly reionization occurred and what role early galaxies played in this process. JWST's data suggests that the first galaxies might have formed and evolved at a faster rate than anticipated, which will require new models of cosmic evolution to explain how these early galaxies could influence the larger structure of the universe. This will be one of the key research focuses in the future. Another surprising finding from JWST's observations is the prevalence of supermassive black holes in the early universe. Astronomers have detected signs of black holes that are much larger than expected for their cosmic age, challenging existing models of black hole formation. The most striking of these findings is the discovery of black holes with masses exceeding billions of times that of our Sun, existing within the first few 100 million years of the universe's existence. The exact mechanisms behind the rapid formation of these supermassive black holes are still unclear. Did they form from the collapse of massive primordial stars, or were they seeded by more primitive black holes that grew over time? Are they linked to the formation of the first galaxies, or do they influence galaxy evolution in a way we haven't fully appreciated? these questions remain unanswered and will require years of investigation. Dark matter continues to be one of the most elusive components of our universe, yet the JWST has already provided valuable insights into how it shapes the large-scale structure of the cosmos. By observing the way light from distant galaxies is bent around massive objects, the telescope has enabled astronomers to map the distribution of dark matter with incredible precision. However, these observations have also raised questions about the properties of dark matter itself. The interaction between dark matter and regular matter, and whether dark matter has any non-gravitational interactions, remains largely speculative. The data from JWST has helped create more detailed maps of galaxy clusters, revealing that dark matter plays a more dynamic role than previously thought. But further investigations will be needed to confirm whether there are still more exotic forms of dark matter yet to be discovered. Looking ahead, the future of space telescopes will not be limited to a singular focus on individual missions. As we have seen with the JWST and its planned collaboration with other observatories like the Roman Space Telescope, the future of astronomical research lies in the synergy between different telescopes with complementary capabilities. While much has been discovered, the journey is only just beginning. The future of space telescopes promises a more detailed, comprehensive understanding of the universe than ever before. It is a future filled with discovery, collaboration, and perhaps answers to some of the most profound questions humanity has ever asked about its place in the cosmos. Well, that's it for now. Thanks for watching. Did you like this video? If you did, please consider liking, dropping a comment, and hitting the subscribe button so that you don't miss out on our new uploads. Also, don't miss this video you see on your screen right now. It's truly unbelievable.